Okay, so let's start this second lecture. First of all, a couple of technical points. I hope no one had problems in playing the recordings. If anyone did, you need a codec, and I've specified the link either on the lecture log or in an instruction file that you can find on BIP. Second thing, the idea of these lectures is to give an overview of many subjects. So, for example, we introduced submanifolds of the Euclidean space last time, and we touched like three different ways of thinking about a submanifold. So as a graph, as a zero, or as something which has local coordinates, which is locally diffeomorphic to an open set of Euclidean space. There is a deep interplay between these three ways of looking to a submanifold, and obviously we didn't investigate any of these. So if you pick any of the books that are in the reference section or any other book about differential geometry, you will find a lot about how to pass from a graph to a zero locus, what are the all the differential geometry ideas we introduced, like the tangent space, the tangent bundle, the gradient, etc., how they specialize in every different way of thinking about that. Now, today, you can see from the background, we are talking about algorithms. And so, lecture 3. Let's start from the Taylor formula. So, the Taylor formula in Rn is a way to approximate a function with sums of homogeneous polynomials. So, you start, you take your function, and, well, I mean, you all know, but you write it out. Like some constant term plus a linear part. So this is in one variable, obviously. And you go on. Now, what happens in several variables? You more or less, up to this point, you more or less probably know also in several variables. This is R. In Rn, what happens is that you have, okay, the first term is the same, so the constant. Now you have the scalar product between, well, that's not. You have these, and the second order term is the bilinear form given by the Hessian matrix of F in X0. And you can go on, and I mean, going on is not exactly straightforward, but more or less. You will have, here you have a bilinear form, you will have a trilinear form, etc., and k-linear forms. Okay, so functions from Rn to R that take a vector, that take, yes, I mean, in principle, n different vectors and are linear in each vector. For example, the determinant is an n-linear form. The point is that if you take the nth derivatives of a function, if you take the first derivatives of a function, you get a vector. The second derivatives of a function give you a matrix, in a way. The third derivatives give you a, well, a cube of numbers, which is called a tensor, and so on. And you apply these, and you could think of them as the coefficients of a homogeneous polynomial in the right number of variables. What you do is that you take the displacement vector x minus x0 and you plug it in the n-linear form given by the nth derivatives. So you take the dot product with the gradient, you apply it to both sides of the Hessian matrix, and so on. Now, the problem on a submanifold of the Euclidean space is that you cannot take the difference between 2 points. I mean, you can. Okay. No. You can. I mean, you take your manifold. You take a point here and a point here. So this is a surface in R3, for example. What's the difference? If this is x0 and this is x, your difference will be, well, not really this one, but a vector parallel to this one. And if you have somewhere the origin, because we are in R3 in this case, you have a vector going out to x0, you have a vector going out to x, and the difference, more or less, is just this random vector which does not end on our manifold M. So this is our manifold M, and we are, for example, in R3. So what happens is that x minus x0 doesn't have any meaning if we want to stay on our submanifold. So what can we do? We need a way to pass between the tangent space, which is where we define, for example, the gradient, and the manifold. From the manifold to the tangent space, we define vector fields. So a vector field is something that takes a point on the manifold and gives you a vector in the tangent space. We need a way back. So this is our first step, defining a retraction. So a first order retraction is a smooth map from the tangent bundle to the manifold. So the entries are, the first entry is the point on the manifold, the second entry is the vector in the tangent space of that point. So if you remember, the tangent bundle is the set of all pairs, point and tangent vector to that point. So we want a map from the tangent bundle to M such that if you take the 0 vector, you stay in the point. And if you fix X and consider the map from the tangent space to X to M, so X is fixed and you vary V, the tangent vector, this map, which is from a k-dimensional vector space to the manifold, this has to have as the differential the identity. What does it mean? I mean, this is it seems a strange condition, but what does it mean? It means that this is the reason for first order here. So it means that you have a way to map the tangent space of a point to a manifold, to the manifold. It sends the origin of the tangent space to the point, and you want that it looks like the identity nearby. So, for example, let's see, the easiest example maybe is, for a mathematician, the easiest example would be with a vector space, because the tangent space to a vector space is the vector space itself. But let's be less idiotic. We take the sphere, so I don't think you are surprised by the fact that the tangent space for the sphere, the point x, is just the set of all vectors in Rn which are orthogonal to x. So x is your radius, the tangent space is just the space orthogonal to the radius. What does it mean to define a retraction? We have our sphere. This is the point x, this is space Tx to Sn minus 1. And we want a way to send these, well, not really this is not, I mean, this is a drawing, but technically the tangent space is a vector space, so it goes through the origin. Now, we need a way to send this space to the sphere, sending the origin to x. The easiest way you could think of is the following, at least. You take x, you add the vector of the tangent space, so this is x. This is, for example, a vector of the tangent space. If you sum those, you end up with a point which is here, which is not on the sphere. It's on the tangent plane. So how we end up on the sphere again? We just divide by the norm. If we divide by the norm of the vector, we are projecting it to this point which is on the sphere because it has modulus 1, and it, in a sort of way, is you are bending the plane on the sphere. Now, we should verify that the differential of this map is the identity. You can, I mean, you fix x, so you want to take differential only in V. I mean, it's a computation, so. An easy one, because it's a computation just in an I mean, it's calculus 2. It's not difficult. Okay, so this is an example with the sphere. So this is a sort of thing we are interested in. Now, if you fix a tangent vector to a point, you can take the line that's spanned by that vector, and you can retract the line on your manifold. So you end up with a curve, starting from the point, and going in the direction of that tangent vector. So the second hypothesis ensures you that the tangent vector to the curve you obtain that way is exactly v. So you take the retraction, x is fixed of tv. So you take a vector on the tangent space and the line that goes through it. Moreover, the second request guarantees that the differential is invertible in 0, and so it's invertible in a neighborhood, so it's a local diffeomorphism between, it's a parametrization of your surface, of your manifold in general. Okay, why do we need something like that? Consider that curve. So take your tangent space, take a line through the origin, and retract it on the surface. So if you think of the sphere is really a retraction, so you're pulling things towards the origin. Take that curve and retract it on the sphere. Now you take any function f and you evaluate it along the curve. You can write the Taylor expansion for f along the curve. So it's a one variable Taylor expansion. The result is the following. You have the value of f in x plus the displacement t times the scalar product between the gradient along the manifold times the vector plus some negligible term. So this is exactly your usual first order approximation. Now, what does it tell us? It tells us, we cannot use these to approximate the values of the function because we don't know how to end up in another point. So if I give you x and another point of the manifold, you don't know which curve you have to take to go to the other point. Which of these curves, which of the curves written like that? Maybe there is no curve that goes there. You don't know. What you know is that these, if you stay close enough to the point, you reach every other point because it's a local diffeomorphism. So you can study a local behavior of the function. That means that a point is a critical or stationary point for f if and only if this quantity vanishes, which is what we saw also the last time. Now, with these ingredients, we can write down a first-order optimization procedure. Now, question. Do you all know what a gradient descent or Newton algorithm is in the usual context of real functions? Is there anyone who doesn't know? So, just roughly, the idea is that if you want to find a critical point, let's say a minimum here, and you start somewhere else, what you can do is slide along the curve. So, for example, here you are looking for the minimum of a function of one variable, which has this graph. Here the gradient, the derivative is negative, so we are going down. If we follow the derivative up to a point, we end up in somewhere here, for example. Obviously, as we go toward the minimum, the derivative will go to 0. So, in principle, if we take steps which are proportional to the derivative, at some point we will stop, hopefully, in a stationary point. So we take another step, we go, and we go here. And the steps we take are smaller and smaller because they are proportional to the derivative at each point. If this is like a quadratic function, the derivative goes linearly and goes to 0 in the minimum. So slowly. And at some point, you end up really close to the stationary point. Again, hopefully. I think you all studied the convergence of this kind of algorithms, etc. So what's the problem when you have a constraint? In one variable, it doesn't mean anything. But in several variables, you can maybe have a constraint. So something which is analytically solved by a Lagrange multiplier system. What you do in that case? Well, it's difficult because the gradient is now a vector, it's not just a number. And you want to follow the gradient. You want to follow the gradient or else the negative of the gradient, sorry, to the minimum point. What's the problem? If you want to stay on some submanifold and your function is a function defined on the space, the gradient, I mean, in general, won't be along the submanifold. It will force you to go out the submanifold. So, this is the problem with the gradient descent when you have some constraint. This whole theory of manifolds, submanifolds, whatever, gives you a way to write algorithms that work smoothly with constraints. So we have a submanifold, a function, the cost of our optimization, and we want to find the minimum. Okay, well. Now, we can twist the usual gradient descent to adapt it to the manifold situation. The word Riemannian here will be clear later on. I mean, like in 4 or 5 hours. Not today, obviously. Okay, this is not. I mean, this is code just to have the syntax highlight, but it's not proper code. It looks like Python, more or less. So, what are we doing here? We have this function, which is a Riemannian gradient descent. We have to pass to it the retraction, which encodes all the information about the manifold, in fact. A starting point, our guess, and the cost we want to minimize. So we produce a sequence of points starting from x0. We initialize some stuff like the sizes of the step, the displacement vector, the iteration counter, a lot of things. And we have a stop condition. Now, while the stopping condition is false, we do the following. We compute a step size. So a step size means, you remember before, I told you that we move proportional to the derivative, proportional to the gradient. Not exactly off the gradient, but proportional to it. So we need something to multiply the gradient by. And this is our step size, which depends on all the previous points and all the previous step sizes, and obviously on the function, in principle. Next, we calculate the displacement vector. So we take the gradient, the Riemannian gradient of f along the submanifold. So we need to have a gradient function which depends on the submanifold, which is written exactly for the submanifold. We multiply it by our new step size, and we put a minus in front. We have our displacement vector. Now the displacement vector lives in the tangent space. We want to go back to the manifold, so we use a retraction. So the next point is the retraction, starting from the point xk, so the last point, that moves of the vector sk. Now we just have to check if our stopping condition is satisfied or not, usually if our point is close enough to whatever, and we increment the counter. Okay, this is just. When the stopping condition is met, so for example, if the gradient is small enough or something like that, we exit from the cycle and we return the point and the value. So this solves both mean and argmin problem, but anyway. Obviously, this is far from being a working algorithm. We have a to-do list. So determine a step size function, determine a retraction function, and a check exit function. Okay, the retraction, it depends on the submanifold we are working on. The exit, it's technical. I don't want to dwell in it because it's more or less the same as in the Euclidean case. The step size also, but I mean, it's interesting. So we will be talking a bit about the step size. Now, this algorithm needs some favorable conditions to work. So we have some assumptions to make. Okay, first of all, our function is bounded from below. This is just reasonable, to common sense to ask for a minimum. Second assumption, at each iteration, there is what is called sufficient decrease. So there exists a constant such that the gradient times the constant is a lower bound from the difference between the values in each step. So we are decreasing enough at every time. Obviously, not in absolute terms. We cannot ask that every time we decrease the value by 1/10. It doesn't make any sense. We need a condition that depends on the behavior of the function. So that's why there is a square norm of the gradient. And then a rather technical condition. There is a subset of the tangent bundle, so a set of pairs of point and vector, for which there is a constant such that this estimate holds. What does it mean? Okay. In Rn, we are saying that f of x plus v is less than or equal of f of x plus v times the gradient of f at x plus this error term. So we are asking that the error term, or if you want, the difference between f and its first order approximation is bounded by some constant. And we are asking it for a set of points and a set of tangent directions. So in the end, on a small set in principle. So locally around x could be enough. Okay, maybe you can see that this is the same condition if we are just in Rn. And this happens, I mean, this is an exercise in calculus. This happens if and only if the gradient is Lipschitz. So I think the L is exactly the Lipschitz constant. I mean, I should, to be sure, I have to do the computation. I don't want to, but we are asking something like that. So that there exists a constant C such that this holds true, which should be L or L over 2 or something. I don't remember exactly. Now, obviously, this can be false on all over Rn, but if f is enough well behaved, for example, if you can differentiate f 2 times and you get a continuous function, then okay, this is locally true. So again, assumption 1 is common sense. Assumption 2 is given by a suitable choice of the step size function. Assumption 3 is a substitute for the Lipschitz condition for the gradient. That's what I just told you. So assumption 1 depends just on the problem we ask, on our cost function. Assumption 2 can be obtained if we choose carefully the step size. Assumption 3, again, is something which, is something which depends on f. In Rn you don't see it, but also on the retraction. In Rn you don't have the retraction because the way of moving from a point in a direction is just you sum the point and the displacement vector. But on a manifold, here you have a dependence also on the retraction function. So changing the retraction function can give you different sets S and different constants L. By the way, normally you don't know L explicitly. You know that some L exists on some subset. And you have conditions so that everything is enough. So obviously you will have theorems that say if every step of the Riemannian gradient descent stays in S, so if every new point and every new gradient is in the set S, then we know that. And many times you can show that there exists maybe a global L for the whole of the tangent bundle, but it's not, I mean, it really depends. Now, step size, line search algorithms. The procedure to pick the step size is called line search. And you can formulate it as finding the minimum of this G function, which is a function only of the real number t which appears here. So you fix xk, you fix this vector, which is the gradient, but you fixed it, and you want to minimize this function in T. Okay, you have three strategies. Fix step size. And as stupid as it may seem, there is a choice, which is this one. So this works. This gives you convergence, sufficient decrease, and whatever. The only problem is that usually L is huge. Maybe it's huge just because you have some part of the manifold, some part of the tangent bundle, which gives you issues, and so you have to pick a very big L. But if you restrict to other parts, L can be much smaller. Or if you just are going in another direction in the tangent with the tangent vector, L can be picked smaller. And this is difficult to explicitly calculate. So the estimates you get from L give you usually a very small step size, which you don't want, because if it's too small, it will take forever to converge. Now, something which rarely happens is that you can exactly minimize G of t. It almost never happens, but sometimes, I mean, if you're lucky, if the combination of the cost function and the retraction is very nice, for example, is convex. Because remember, now G is just a real function of one variable, so it's a function on R. I mean, it can happen that combining the things, it ends up being convex or quadratic even, or something like that. The usual is backtracking. So you guess an initial value t0, and you improve it iteratively until it is good enough. How? Well, with what is called the backtracking algorithm, which is very easy. I mean, it's almost laughable, because the only complicated thing is the condition you are checking. So now, forget the condition for a moment. What you're doing is that you initialize t equal to t with t naught, and every step you multiply t by a fixed amount, which you usually pick up, I don't know, I mean, a number between 0.5 and 0.8, something like that. Now, you can see that here there is another parameter, which is r. So x0 is the point, t0 is the initial guess, f is the function, the retraction, and you have, okay, t0 is a parameter, h, the quantity you multiply t by every time, is a parameter, and r, which appears in this condition, is again a parameter. Now, let's write down the condition more properly. So, this is called the Armijo-Goldstein condition, and you exit from the loop if this is true. So, here I'm checking the opposite. So I exit if this is true. I exit if the decrease I obtain is greater or equal than this quantity. Now, this is not a uniform quantity. It depends on t, and t varies at each step, because the backtracking algorithm improves t every time. So we loop the gradient descent. At each passage, we loop the backtracking until we meet this condition. R is usually really, really small, like 10 to the minus 4, 10 to the minus 3, something like that. So we are actually asking that there is a sufficient decrease at that step. Now, if you have assumption 3, you can extend this local sufficient decrease to the whole of your gradient descent. Also, something which I won't be going into now, but with L, you can estimate how fast the gradient goes to 0, how many times you have to loop in this backtracking algorithm at each step. You can get, obviously, an upper bound. And you can also estimate how fast the convergence is. Now, things we didn't pay attention to, but we should have. How to pick T0, the initial guess of the backtracking algorithm. This is the first question one could raise in this picture. Then, how can I ensure that the convergence happens near critical points, and how fast is this convergence? Given second order conditions, you can, if you studied the Euclidean case in some numerical analysis or whatever is the name of the course, you know that if you have some information about the Hessian of your cost function, you know that there is convergence, and you know that the convergence rate is linear. At most. There are similar conditions also here, but if you remember the last 5 minutes of the second lecture of Tuesday, they were a mess because the Hessian in the Riemannian setting is really, really a complicated object. So we will get back to this in when we will be doing the second order geometry of manifolds. Now, how to compute the gradient? The usual way to compute the gradient, you will be working with, okay, this may seem weird, but what I had in mind when I wrote it, you usually will be working with matrix manifolds. So, for example, we will see it the next hour. For example, the rotation matrices or the Stiefel manifolds or the Grassmann manifolds, or worse things. So there are the symmetric matrices, the fixed rank matrices. So you have a function which is defined on matrices. And so the computing the gradient means to move a bit inside the matrices, which can get complicated. So the usual way of doing it is compute directional derivatives on the manifold and find something which looks like the element which gives you that linear functional by scalar product. Also, this is just an observation, not a question. You can numerically check the gradient via the Taylor formula, via actually the remainder of the Taylor formula. I'm not going into this again, but I want to say that. By the way, this is a very rough sketch of all the idea behind the Riemannian gradient descent. In the references for the course, there is a book which is freely available online by Bumal, Optimization on Manifold, something like that. And he gives a great introduction to the Riemannian geometry and also a lot of worked out examples for matrix manifolds and cost functions that you could happen to see, etc. And I think it contains the proofs of all these statements. So if you want to see the proof, or better, maybe you don't care about the proof and you could be almost right in thinking that, but if you want to see how, for example, where was that? Here, how, for example, the Lipschitz condition gives you the global sufficient decrease and how the Lipschitz condition gives you the rate of convergence and the estimate on the number of loops you need, that reference contains the precise statements. And it's written in these terms, so it shouldn't be too difficult to read that after having read these slides. And I think that is all I wanted to say about these topics. So if you have any questions, is there anything unclear?
What is the role of the retraction?
Okay. Well, it depends. I mean, the retraction, you need the retraction because it's okay. So up to now, every retraction works, and I've called them first order retractions because there is that condition about the identity. So up to now, every retraction works. The difference is that in principle, you need, I mean, the retraction plays a role when you prove things like that. If you want to pass from this condition to the global sufficient decrease, you need to have some control about the retraction. Also, the third assumption involves the retraction. So, for example, here you have to find S and L will depend, well, L will depend on S, and they will both depend on F and R. If you change the retraction, you could change the set S and the constant L.
So you change L and S, but I mean, can you be sure that L and S exist for each retraction?
Well, you can prove some compactness. If you have some compactness argument, yes. Because you have a set, there is some S inside the tangent bundle. It may be a very small S and so useless for your purposes, but in principle, yes. So every theorem at this point has always the hypothesis if the sequence of points and gradients given by your algorithm is contained in S, then. For example, for the retraction I wrote you on the sphere, you can find a global constant. I don't remember the number, but for the retraction I wrote for the sphere, you can find a global constant that bounds everything on the whole tangent bundle. But you can change the retractions. Also, where was it? Here, under some second order conditions. If second order conditions comes into play, you want more control on the retraction. So we will be talking about second order retractions at some point. If you want to be sure and you know what it is, you can take the exponential map. But in general, varying the retraction gives you different results. We will see it in the next lecture, by the way. I've not written it, but there is an example. Okay, so any other questions? If not, I stop